Nobel Foundation, I would like to welcome you to this year's prize award ceremony. I would especially like to welcome laureates and their families to this ceremony whose purpose is to honor Nobel Foundation, I would like to welcome you to this year's prize award ceremony. I would especially like to welcome laureates and their families to this ceremony whose purpose is to honor the laureates and their contributions to science and literature.
Yeah, and now time for David Wineland.
I think the thing that has always interested me and continues to interest me is that even when I was first exposed to physics in my high school class, what I liked about it was that relatively simple math, at least simple for mathematicians, can be used to explain how the world works.
Selamat pagi, salam sejahtera. Good morning, everybody. We will start our talk while we in a while, 10:30. We will await the main speaker, Professor David Wineland, as well as others to join. Thank you. Please hang on. In the meantime, please have a look at our running videos.
Nobel Foundation, I would like to welcome you to this year's prize award ceremony. I would especially like to welcome laureates and their families to this ceremony whose purpose is to honor the laureates and their contributions to science and literature.
Yeah, and now time for David Wineland.
I think the thing that has always interested me and continues to interest me is that even when I was first exposed to physics in my high school class, what I liked about it was that relatively simple math, at least simple for mathematicians, can be used to explain how the world works. And so I would certainly put quantum mechanics into this relatively simple math. And what I like, or certainly one of the things I like, is just the fact that when we do our experiments on these quantum systems, these atoms, we can use quantum mechanics to explain, what goes on in the experiments, and this connection between the theoretical explanation and actually doing the experiment is still, I still really like that aspect. So. We're always trying to find ways, of course, to improve the clocks, and sometimes that does involve stepping back and saying, well, where does, we can't use the standard practices to do things. We need to try to invent new ways to do that. A good example of this is when I came to NIST after a couple of years being here. My boss at that time, Helmut Helvig, was able to get us some money to try to do laser cooling. And laser cooling is important because one of the effects that shifts the observed frequency of the atoms that we look at is the so-called time dilation shift. And this comes from Einstein's theory of relativity, where time for moving objects goes slower than it does for stationary ones, and this effect occurs at a very small scale with the atoms that we look at, but it's an important one, and we have to correct for that. So, one of the other areas we've been exploring is the idea of making a quantum computer, and it turns out that one of the fortunate things is basically all the techniques we use for clocks are applicable to trying to manipulate atoms for a quantum computer. To implement the ideas of making a quantum computer, it turns out that we need to have an extreme form of cooling. So we basically have to completely freeze out the motion of our trapped ions, only limited by the limits of quantum mechanics. That is, we put them in their so-called ground state of energy. And this was this level of cooling wasn't so necessary to achieve the accuracy that we needed for the clocks, but it was critical to be able to manipulate the atoms to try to make them as quantum bits or qubits. And so we had to develop a technique, and we're first to demonstrate that we could actually put the atoms in the ground state of their motion. With this idea of superposition, we can put our atoms, our ions, in these states where they're simultaneously both a 0 and a 1 at the same time. Now why this gets interesting is in this superposition sense, we can, with 300 bits in a classical computer that could store maybe a line of text, our quantum computer that can store more has more memory elements than if we took all the matter in the universe and made a classical memory that way. So it's this exponential scaling that gives this potentially very high ability for memory, and also turns out that we can operate on all these bits, all these numbers at once with a single operation. So in some sense there's this property of massive parallelism, and that's what we're trying to take advantage of. Quantum computers are not going to replace classical computers. In fact, we already need a fairly sophisticated classical computer to run our simple quantum computer. But there are certain specialized problems. And around 1995, Peter Shor, a computer theorist, came up with the idea. He showed that if you could make this quantum computer, he came up with a computing algorithm where you could efficiently factorize large numbers. Well, that may sound a little esoteric, but basically all modern encryption systems, when you buy something with your credit card on the web, and it's encrypted, basically all these encryption systems would be compromised if you had the ability to efficiently factorize large numbers. But what's I think more interesting for scientists is the application, physicists in particular, is the potential application that we might use this, even a small quantum computer, to simulate other quantum systems. So an example would be of this, maybe popular today and timely today, is that people are all excited about seeing the Higgs particle. These particle systems are already so complicated. They may not involve more than tens of elementary particles, but there are so many particles that our classical computers can't solve the quantum dynamics that goes on in these systems. And the fact that we're more generally trying to develop methods of metrology, measurement, that are limited only by quantum mechanics. So, that our work on trying to make a quantum computer, everything we need to do that for those experiments also improves our ability to do metrology.
Nobel Foundation, I would like to welcome you to this year's prize award ceremony. I would especially like to welcome laureates and their families to this ceremony, whose purpose is to honor the laureates and their contributions to science and literature.
Yeah, and now time for David Wineland.
I think the thing that has always interested me and continues to interest me is that even when I was first exposed to physics in my high school class, what I liked about it was that relatively simple math, at least simple for mathematicians, can be used to explain how the world works. And so I would certainly put quantum mechanics into this relatively simple math. And what I like, or certainly one of the things I like, is just the fact that when we do our experiments on these quantum systems, these atoms, we can use quantum mechanics to explain, what goes on in the experiments, and this connection between the theoretical explanation and actually doing the experiment is still I still really like that aspect. So we're always trying to find ways, of course, to improve the clocks, and sometimes that does involve stepping back and saying, well, where does, we can't use the standard practices to do things. We need to try to invent new ways to do that. A good example of this is when I came to NIST after a couple of years being here. My boss at that time, Helmut Helvig, was able to get us some money to try to do laser cooling. And laser cooling is important because one of the effects that shifts the observed frequency of the atoms that we look at is the so-called time dilation shift. And this comes from Einstein's theory of relativity, where time for moving objects goes slower than it does for stationary ones, and this effect occurs at a very small scale with the atoms that we look at, but it's an important one, and we have to correct for that. So, one of the other areas we've been exploring is the idea of making a quantum computer, and it turns out that one of the fortunate things is basically all the techniques we use for clocks are applicable to trying to manipulate atoms for a quantum computer. To implement the ideas of making a quantum computer, it turns out that we need to have an extreme form of cooling. So we basically have to completely freeze out the motion of our trapped ions, only limited by the limits of quantum mechanics. That is, we put them in their so-called ground state of energy. And this was this level of cooling wasn't so necessary to achieve the accuracy that we needed for the clocks, but it was critical to be able to manipulate the atoms to try to make them as quantum bits or qubits. And so we had to develop a technique, and we're first to demonstrate that we could actually put the atoms in the ground state of their motion. With this idea of superposition, we can put our atoms, our ions, in these states where they're simultaneously both a 0 and a 1 at the same time. Now, why this gets interesting is in this superposition sense, we can, with 300 bits in a classical computer that could store maybe a line of text, our quantum computer that can store more. Has more memory elements than if we took all the matter in the universe and made a classical memory that way. So it's this exponential scaling that gives this potentially very high ability for memory, and also turns out that we can operate on all these bits, all these numbers at once with a single operation. So in some sense there's this property of massive parallelism, and that's what we're trying to take advantage of. Quantum computers are not going to replace classical computers. In fact, we already need a fairly sophisticated classical computer to run our simple quantum computer. But there are certain specialized problems. And around 1995, Peter Shor, a computer theorist, came up with the idea. He showed that if you could make this quantum computer, he came up with a computing algorithm where you could efficiently factorize large numbers. Well, that may sound a little esoteric, but basically all modern encryption systems, when you buy something with your credit card on the web and it's encrypted, basically all these encryption systems would be compromised if you had the ability to efficiently factorize large numbers. But what's I think more interesting for scientists is the application, physicists in particular, is the potential application that we might use this, even a small quantum computer, to simulate other quantum systems. So an example would be, this may be popular today and timely today, is that people are all excited about seeing the Higgs particle. These particle systems are already so complicated. They may not involve more than tens of elementary particles, but there are so many particles that we don't have. Our classical computers can't solve the quantum dynamics that goes on in these systems. And the fact that we're more generally trying to develop methods of metrology and measurement that are limited only by quantum mechanics. So, that our work on trying to make a quantum computer, everything we need to do that for those experiments also improves our ability to do metrology.
Selamat pagi, ladies and gentlemen. Good morning. We're still waiting to settle some technical issues. Please give us some time. We will start shortly. Thank you.
Nobel Foundation, I would like to welcome you to this year's prize award ceremony. I would especially like to welcome laureates and their families to this ceremony, whose purpose is to honor the laureates and their contributions to science and literature.
Yeah, and now time for David Wineland.
I think the thing that has always interested me and continues to interest me is that even when I was first exposed to physics in my high school class, what I liked about it was that relatively simple math, at least simple for mathematicians, can be used to explain how the world works. And
All right. Good evening, Dave. You're in. Prof. Dave, can't see you. Your video is off. Yeah, I know.
I think Dave is here, but the microphone is off.
Dave
He's
is here.
muted.
Yeah, it's muted. Yeah. Good evening, Dave. Could you hear? Can you hear me? Your video and your audio are mute. Video is off and audio is muted. You can join now. Video audio.
Foundation, I would like to welcome you to this year's prize award ceremony. I would especially like to welcome laureates and their families to this ceremony, whose purpose is to honor the laureates and their contributions to science and literature.
Yeah, and now time for David Wineland.
Yes, let's see. It says my host disabled participant screen sharing.
Shah, the host is disabled. He's not co-host. Yeah, okay. All right.
Can you
Yeah,
see part of
we're
my
in.
first slide
Yes.
now?
Yes, yes.
Okay.
All right.
Okay, good.
All right. That's nice. All right. Just give me a few minutes, Dave. I'll read out your bio and we can start.
Okay.
All right. Salam sejahtera and selamat pagi and a very good morning to all gathered here virtually. This is our 15th ISICS gathering, thanks to the
Recording in progress.
non-ceasing efforts of Doctors Nazri Halif and Sharifah Nur Faizah. Thank you to UNIMAP Vice Chancellor, Prof. Zaliman Sauli, and Deputy Vice Chancellor of Research and Innovation, Professor Riza Fandi, and their respective officers for supporting this UNIMAP STEM effort, and to the broadcast control team here for disaster mitigation. And a very good evening to our distinguished presenter, Professor David Jeffrey Wineland. Before we hear him, I would like to wish him a pre-birthday, happy birthday, which is due this Saturday. Happy birthday, Dave.
Thank you.
Dave Wineland received a BA degree from University of California, Berkeley in 1965 and a PhD from Harvard University in 1970. Following a postdoctoral position at the University of Washington, Seattle, he joined the Time and Frequency Division from 1975 to 2018 at the National Institute of Standards and Technology, NIST, in Boulder, Colorado, where he was a group leader and NIST fellow. He is now Philip H. Knight Distinguished Research Chair and Research Professor in the Department of Physics at the University of Oregon, Eugene, Oregon. Since graduate school, a long-term goal of his work has been to increase the precision of atomic spectroscopy, or more specifically, the measurement of the frequencies of atoms' characteristic vibrations. This research has applications towards making better atomic clocks and has led to experiments that enable precise control of atomic energy levels and atomic motion. Such control can be applied to metrology, whose precision is limited only by constraints of quantum mechanics, and to demonstrations of basic building blocks of a quantum computer. For this work, he shared the 2012 Nobel Prize in Physics with Serge Haroche from Collège de France, Paris. Prof. Wineland is married to Sedna Quimby Wineland, and they have 2 sons. And to our viewers out there, if you wish to ask questions or type them in the chat, you are most welcome, but please wave or raise a hand or chat it in. Thank you. Prof, the Zoom is all yours now.
I hear other voices. Anyway, well,
right.
so I should go ahead, huh?
Yes, yes.
Okay. Well, you can see my title there, and from what the last 10 minutes, I probably don't know much about regular quantum computers, so I'll try to tell you a little bit about those. So anyway, one quote I liked, it was from Schrodinger, and he said, he wrote in 1952, "We never experiment with just one electron atom or molecule. And in thought experiments, we sometimes do. This invariably reaches ridiculous consequences." And I think he's referring there, the ridiculous consequences were Schrodinger's cat that many of you may know about. And I won't go into that, but it's a macroscopic entangled state. Anyway, but these days, in fact, thought experiments for example, with individual atoms are certainly what we can work with. And to do that, to work with individual atoms, we need precise control and typically isolation from the environment, because quantum systems tend to be fairly fragile. And some examples are of the kind of control we have, or that results in atomic clocks, and we're starting to exercise some of the basic ideas of quantum computers now. And certainly, there's many people and groups involved worldwide, and in fact, there's approximately there's a list of about 100 groups that are just pursuing the ideas of quantum aspects of quantum computing, just with trapped atomic ions. So we're just one part of this. So
Dave,
anyway,
Dave, Dave, sorry. If you don't mind, could you turn on your video camera, please?
Turn what?
Your camera, your video.
Oh, sorry.
The video is off. Yeah, we can't see you.
I can't remember. Let's see. Well, I'm sharing screen. Okay. Oh, let's see. Maybe that'll do it. Is that
Yes. All right. That's nice. All right. Carry on, Dave. Carry on.
All right. So anyway, the basic tools we'll be working with here are ion traps, and the basic I mean, I could explain this to the students, all the students, but it takes a fair amount of going through that. So I can't give you the details, but the thing to just know is that if we have an electrode structure like this, we can apply a combination of RF and static electric potentials to this device, and we can basically, for a charged particle, we can create a three-dimensional harmonic well. And actually the person that developed what we call RF traps was Wolfgang Paul, and he shared the Nobel Prize for his work in developing this. So anyway, but without going into the details of this, what you can think about is an analog, classical analog of what the trap does is it provides our classical 2D analog is like a marble in a bowl, and yet we're confining in a three-dimensional harmonic potential. So at NIST, I'm going to tell you a little bit about experiments we did on mercury ions, and this shows a schematic here. And so what we're using lasers to excite certain transitions in our ions. One of the ones that's interesting for mercury is I'm using atomic physics notation here, but you won't have to worry about that too much. But this would be, say, the lowest energy state of the electrons in the ion. And we can find a transition. This is in the ultraviolet, about 194 nanometers, where we can excite we can excite the ion from a lower energy state to a higher one. And the lifetime of this upper level is only about 2 nanoseconds. So we can scatter a fair amount of light off the ion, and this is what we use to detect what we're doing with the ion. So if we have a single ion, we can actually make a picture. And here's this is we can't, of course, with our eyes we can't see 194 nanometers. It's too far in the ultraviolet. But so we had actually a fairly crude video camera that is much cruder than the ones you can buy at the store. But nevertheless, we could make pictures where you could see a single ion at the center of the trap here. And just sort of a little interesting side note, you can see the dimensions here of the internal part of the trap are about 1 millimeter. And we can actually, by doing auxiliary experiments, we can show that the actual size of the ion, that's wave packet, is about 100 times smaller than the size of this dot you see in the screen, which is the ion. And the reason for that is just that the optics is not good enough to focus better, to get a sharper focus on the ion. Well, for these experiments on quantum information, we're also gonna use another level in the ion, and this level here is fairly long lived. It lives almost in a second, and so one way we can tell when we make the transition here, well, I should say, in terms of the quantum computer, what we can think about is we can actually, because this is so long lived, we can actually make a classical qubit. We can store the atom in the ground state, or at least for a short amount of time, we can store it in the D state. And this makes a classical a bit, just like the zeros and ones in our computers. But the basic idea is we can also make superposition states of the based on these two states. And I'll say a little bit more about that now. And so the one analog I like, which is totally classical, but I think it'll give you an idea of superpositions and what happens when we do measurements. So if we look at this image of this box, sometimes I think most of us will sometimes we'll see this face be in the foreground, and other times maybe we'll see this face be in the foreground. And so you can say there's an ambiguity about whether this thing here is in that state or that state. And in fact, the idea of superposition is it can be in both states at once. So the box up here possesses both these properties, and that's the idea of superposition. And when we measure our superposition, and as I say, most people can get to a point where this image will collapse on one of these two orientations, and that's very much like when we do a measurement on an ion that might be in a superposition state. We call that collapse or projection into one of the two states of the box or the states of the atom. So actually, another thing. I mean, superposition is kind of a weird concept, and one thing we can do in the lab, sort of to show that weirdness of superposition, we can have one ion in the trap, and in this the marble in the bowl analog, it'll be oscillating back and forth. But we can also make the states of the ion where at certain times it's both on the left side of the bowl and the right side of the bowl at the same time. And this, of course, makes no sense in our ordinary day experiences, but this is the world we live in when we play with these quantum systems. So I'm going to talk about this example of an optical qubit. In this case, it's one of our first experiments on these lines was on mercury ions, and so mercury has there's this third level in the atom state. So this is this strong ultraviolet transition. But if this is now, if these two states make our qubit, and if we have it in a superposition state, which is shown by this box here, and for those that aren't familiar with the quantum notation, these arrows are represented just ways of representing two states in the ions, and I've shown graphically what they are here on the left side of the figure. And the coefficients out front of these individual wave functions, we call these amplitudes, and the square of the amplitudes give the probability of when we shine on our detection laser, and I'll say that in a minute, if the ion will collapse into either what we tend to call these spin up and spin down. And the reason for that is that a spin 1/2 particles has two levels. And so we often, in atomic physics, label these as just spin up and spin down. Anyway, but of course, when we do the measurement, of course, the total probability of measuring either the spin down state or the spin up has to be 1. And so now I say a little bit about logic gates for processing. And so that I think there's, again, a little bit simplified picture, but what we can if we look at a classical bit, we know we can store information as zeros or ones. But it turns out that it may not be the most efficient way, but with a classical computer that just has two operations, let's say a bit flip and so-called AND gate, which has the truth table over here on the right, then in fact we can do universal classical computation. As I say, it may not be the most the most straightforward way or the fastest way to do computation, but all we require in a classical computer are these two operations. We can do any classical that's normally done on a computer. And there's an analog in the quantum world where we need also two basic operations. And the first one we call a rotation. And I was using this idea of a spin 1/2 particle. The direction of the angular momentum is like an arrow which can point in any direction. And we tend to make this analogy with spin 1/2 particles. And the idea when we call a rotation is if the electron, in the analogy of the electron spin, if it's pointing up, it's where we can make the angle of that angular momentum vector be anything in space and what we want. And that we call this a rotation. It's given these are the coefficients we can describe the angles in space that it's rotated about. And of course, because the square of the coefficients have to be 1, we can easily make that. We can make that criterion by describing these with the amplitudes with these cosine functions. And then it turns out again, as in the case of a classical computer, if we make a quantum computer, we can do all possible computations with just having this rotation operator and a sort of a non-trivial logic gate. And in this case, it looks like almost this is the truth table for this one example of a logic gate. In this case, it looks like it's not really doing anything except this one state for this particular gate picks up a minus sign. And the reason that's important is that in a quantum computer, we're going to be interfering amplitudes of all these of our qubits, and this minus 1 is like a pi phase shift, and so anyway, we can. I guess the basic message I want to say is that we have, similarly to the classical case, if we have this one operator, the accolade on single spin 1/2, and we have one logic gate like the one I've shown here, then the theorists have shown we can do general quantum computations. And so this is just an example. I'll say again. So if we start the atom in the lower state and then we make a superposition by driving this transition for a certain amount of time, then the way we can tell whether or not we've made the transition is that if we turn on this laser and see fluorescence with this, we will see the fluorescence with a probability getting by the first amplitude squared. If it makes a transition to the excited state, then we don't see any fluorescence. But we have those two binary signals to tell us when we detect a qubit. So what's gonna the thing that at least for the trapped ion case, that what's going to be interesting, we need some other states, and the ones we tend to think about is that are the quantum states of motion. So again, coming back to our classical picture, like our marble in a bowl, we know that for a quantized harmonic oscillator, it actually has discrete energy levels. And I'm labeling these by the symbol M is just for motion. But the idea is that these harmonic oscillator states, they basically is a semi-infinite number of those. And we're going to be interested in working with the very lowest energy states, the ground state and the first excited state. Sorry? Oh, okay. I thought someone was saying. Anyway, so this is
the general scheme then is that the levels we're going to be interested in are the atomic states given by these labels, and then the motional states corresponding to each one of the internal states. And so one thing we want to do is, it turns out we want a nice starting point, and the idea is we want to be able to cool the motion down basically to its quantum mechanical ground state. And the way we can do that is if we shine a laser on this transition here, but it connects this, say that for this example, say the second excited level of motion, and we can actually drive it up to the first excited state of motion in this upper state. And when the atom decays, it actually, with high probability, decays down without changing the quantum number. And so basically with this process where we can first excite the internal state up, but we reduce the motion state by 1, then in this overall process, then we've reduced the quantum mechanical motion by 1. And we can just repeat this process. In fact, we literally just leave the laser on, tuned to the transition that causes the transition up, and then when it decays, it does primarily without changing the motional degree of freedom. And anyway, we just repeat that, and eventually the atom will go back down to the ground state. And so this is the starting point for all of our experiments. Whether we're using one ion or many ions, we want to get down to the quantum mechanical ground state of the motion. So just a little bit of history. I digress here a little bit. Was that in the International Conference on Atomic Physics, it was held in 1994 in Boulder, Colorado, and I was one of the 2 organizers for the meeting. And the ideas of quantum computing were just starting to surface. And anyway, so Peter, I'll say a little bit more about Peter Shor in a minute, but he came up basically with an algorithm for efficient number factoring. I'll say a little bit about that in a minute too. But anyway, at the meeting we invited another professor who was Arthur Eckert, who was in Singapore at that time. Anyway, he knew about Peter Shor's work, and he's an expert on quantum communication and things. So anyway, we invited him to give a talk about the ideas, and anyway, in the audience there were 2 in the atomic physics world, 2 of our favorite theorists, Ignacio and Peter Stoller, who were both at Innsbruck University in the mid-90s. Anyway, they came up with a scheme for how you could actually make a quantum computation using ions. And so the basic idea that they came up, so that I'm showing you a different kind of electrode structure here. And this one here is just such that we make a 3-dimensional harmonic well. But the well along the axis is fairly weak compared to the strength of the wells in the transverse directions. And so if we load, say in this example, or if we load 5 ions into the trap, they all want to fall to the bottom of this harmonic well generated by the electric fields. But because of the Coulomb repulsion between the ions, they line up in a regular array. In this case, we made the strength of the potential very strong in the transverse direction, so they're pinned to the axis of this trap structure, but the Coulomb repulsion holds them apart. And the reason that's interesting is we can then individually address the ions with focused laser beams. So I've just talked about cooling the atoms to the ground state, and so we'll think about where we're going to act on ion number 4 here. And so the first thing we do is we use the basic ideas of cooling to cool the motional states of these ions down to the motional modes down to the ground states. And so the one of the things we can do is we can take a laser that's tuned not quite to the resonance of this narrow transition, but detuned by one by one motional quantum, and so we can convert this this superposition state which was in the spins into a superposition state of the motion. So in some sense, we're mapping the state of this selected ion we're mapping the coefficients of that state into the motion state superposition of the ground and first excited state. So then the next part, sorry. So the next step is to do some logic operation, which will make a logic gate between the motional qubit, which I represent the states of 0 and 1, and the internal state of the ion. So in general, what we can do is we can make, by driving that sideband transition part way, we can make a superposition that looks like this. And so then when we and on the second ion, then we move the laser beams over onto this other ion. So we want to do a logic gate between the first ion was selected and this ion here. So in this case, after we've done the first mapping step, the state of this second ion is going to have some coefficients in front of it that includes both, in general, includes both the upper and lower spin state, internal state of this ion, and the first two motional states. So we've mapped the state we had, the motion and spin state we had on this ion into this ion here. And then the idea is if we take another laser beam, and it turns out if all we do is if for this state here, if the laser is adjusted so it wants to drive resonantly the ion up to this state here, but we leave it on longer, and in fact we just let it go up there and come back down, and it turns out it looks like we've done nothing. But when we do this so-called rotation in phase space, we actually pick up this minus sign, and so this is what allows us to make that two qubit logic gate, but that we wanted for our general operation. So this is the 2 qubit gate we want, and then we can do the other, manipulate the states of each qubit, the internal states, in the way I described previously. So anyway, this is our complete set of gates now. We can in general do any quantum computation, and of course the reality is that we have errors in everything we could do. So this is where the whole field is going right now. We know the basic ideas, but we want to suppress these errors in the operations. So anyway, so pardon me, we were lucky with so this again, this gate was invented by Peter Zoller and Ignacio Serec, and they were at this meeting, and they went away and quickly figured out the scheme for doing quantum logic operations. Anyway, they were nice enough to send us the preprint of their paper on their ideas about this basic quantum computing system. And so actually within a few months after that, we had been doing operations that were similar to the ones I described. And so basically we were able to implement this 2 qubit phase gate, we call it, where we pick up a minus sign on this one state. And then the complete Serec and Zoller gate was done with on 2 ions, was done by Rainer Blott's group in Innsbruck, and we didn't pursue this farther because we've in the meantime found better, more accurate gates. But anyway, this basic scheme would in general do universal quantum computation, we see. So just to give, I can't, explaining Shor's algorithm for factoring large numbers is more like a semester course in this business, but I can try to give you a flavor for what goes on there. And so anyway, the idea is that Peter Shor's idea was it goes along the following lines: is basically, if we want to the idea as a pardon me, what he proposed was a factorizing machine for large numbers. And I should just pause there for a second. The reason that government agencies got in this is certainly these days the most common form of data encryption, secret coding, is done by a scheme which relies, pardon me, the security of the scheme relies on the inability to efficiently factorize large numbers. And for the non-mathematicians, factorizing a large number means just breaking that number into the product of two smaller numbers, which gives the larger number. And it's not his algorithm for doing this is not simple at all, like I say. But the one thing we can, with our logic gates that we do at least in a crude way, we can do general computation. And the idea is we would say this would be the 2-qubit gate, and we'd apply that between ions I and J in this register, and then we could do the rotations on individual qubits, in this case K, and we just run a string of these operations based on these two logic gates to get to factorize large numbers. And as I say, the algorithm is not, you can't get the idea of the algorithm from what I say. It's fairly complicated, but anyway, you'll have to trust me on that. So if we could do these operations, these so-called rotations and 2-qubit operations with high fidelity and a large number of ions, then we could do general quantum computation. And of course, the thing is, we can't do it on very large computations yet so far. And so the other thing, as far as saying, is that we have a long way to go anyway before we can do large numbers, but there's some practical problems, and one is that if we wanted to factorize a large number, we would have to have a large number n of qubits. And the problem is, if I go back to this picture here of the ions, if we tried to load a very large number into this one ion trap, basically we can push the ions close to the center, but basically they would, after a while, this string would buckle and the ions would be pushed out radially. So the main message here is that we have to scale up. We have to think about making a set of these ion traps where we can move ions around, and so that's what this sort of artist view is of the kind of thing we're trying to do, where is that we make several of these we call linear traps, and then if we want to have, let's say, this ion here interact with this ion here, is basically we could bring them down and put them first of all, I say the way we move them around is that in addition to the fields we had for the trapping, we can apply static fields to these electrodes here to push the ions just from the electric fields if we bias these different electrodes. So we can push the ions around along this array of outer electrodes. And anyway, so the idea for a general computation, if we wanted to do a logic gate between this bit here and this bit here, we would bring them down into this lower register, and then I showed red here, but it just means that we brought two ions from somewhere in this register, brought them close together to do a logic gate between those two ions. And so then we'd move these ions some other way to go onto our next step of our algorithm. But this is the kind of thing that at least that people are still. This seems to be, at least for ions, looks like the thing we need to do is be able to move ions around to be able to form different logic gates on the ions for the different ions. And this is a picture of some of the very crude first ideas we we were able to realize. So this is the trap I showed before, and what we can do is we can make a more complicated electrode structure. This is two plates which have these cuts in the electrodes, and we stack these plates together with a spacer that's not shown here. But anyway, we can make in this very simple structure, we can make two trapping zones along this axis, and this is the idea of what what I was explaining on the last page. Of course, it has to be a much more complicated structure. So I mean, just in our first experiments, we just made a few traps had 6 zones, for example, along this axis here, which is it nominally has this geometry here. And so one thing we could do, though, we felt good about, is that we could move the ions around in these traps without disturbing their internal states, superpositions, and that was important for doing the scaling. Anyway, there's been a lot of work been done on these things. In fact, I will say there's now, I won't say much about the end, but there's now about 7 commercial companies that are trying to use these basic ideas to make the quantum computer. Sorry? I'm having trouble understanding.
Sorry. I just found one out. Yeah, sorry. But Dave, on this paper here, on the 2002 paper, when you show RF electrodes, how are the ions cooled? Still by laser?
Oh, wait, no, so I left that part out. So I said how we do a cooling on one ion, and basically when we go into this, in the more complicated situation, if we can cool one ion, and it turns out if it's coupled to all the motional modes, then we can cool the whole system down to the ground state. So that's the basic idea, is that if the modes are coupled, then we just need to cool one of the ions down, and we cool all of them down. So that's how we basically start, So anyway, as I said, the idea is if we will eventually want to scale to very large numbers, and to handle those large numbers, we think about breaking into smaller groups that we could move around and make logic gates and then move somewhere else. Oops. So anyway, I won't, this is shortchanging Peter Shor here, but the basic of it, in principle, the way his algorithm works is that it can be done with a series of logic gates between the two ends, like what I showed with the laser beams, and then the rotations. That's we're just changing the coefficients on one ion. But if we do that, we can string up just a bunch of these operations together, and what theorists have shown is that you can do any general computation. And in Peter Shor's case, he was able to use these basic ideas to at least lay out a plan for factoring large numbers. And so anyway, let's see, where was I here? Okay, yeah, this is shows. Oh, okay, so that's it. I just want to say that there's a lot, as I mentioned before earlier. There's about 100 groups around the world that maybe they aren't trying to build the final quantum computer, but they're trying to take some of these basic ideas and make the devices better, and just even based on trapped ions. And I should say, there's many other potential implementations of quantum computing. One of the most popular ones is to use superconducting qubits based on Josephson junctions, and they are basically Josephson junction is quite a bit different quantum system than these ions are, but you can think about 2-level systems there, and you can think about ways to connect the Josephson junctions basically through superconducting electrodes and superconducting waveline. excuse me, superconducting, pardon me, superconducting electronics that changes the states of the ions. So anyway, we have a long way to go. I would say that we're in this business, but I think we don't see any fundamental roadblocks. And I would say one thing I can say right now is nobody has yet made it. People have done simple algorithms, but there's the most complicated algorithms that can be done on the at least useful ones, can be done on a classical computer. They'd be simulated on a classical computer. Some of you at least paid attention at all. There's some experiments demonstrating quantum supremacy, and that is where they are artificial algorithms where you're not doing anything useful, but you're doing some complicated operation on the quantum bits. And that, some groups, particularly the superconducting groups, have shown there's a real advantage in doing these toy algorithms with superconducting qubits versus a classical machine. So anyway, the most important parts of this I show in this view graph here. This was a group just about the time I left from NIST in Colorado, and on the main purpose of the slide here is just that there's a lot of people working on there. There were at this time there were 5 regular staff people like myself in this group, and we had a lot of students, some postdocs, and some visitors from other countries, and so they were doing all the work on our various experiments. So it was a pretty large enterprise at that time, and still the NIST group is still pretty large. I mean, there's many other groups around the world. I mentioned earlier that there's maybe not groups this size, but there's over 100 groups around the world working on aspects of quantum computing with trapped ions. And I should also mention that at NIST, we were very fortunate. We had some outside support from some of the other government agencies. But I must say, the person that was the laboratory director for most of the time we did these experiments, her name was Catherine Gebry, and she was called the physical measurement laboratory director, and she was really very supportive of us. And so, in fact, she took favor on us. And so if we needed money for any equipment, she was always able to get it for us. And so it was a really great situation. So we were pretty free to select the experiments we wanted to do. So anyway, I mentioned this. Actually, if you want to copy this link down here, this is Rainer Blott's group in Innsbruck, and he has it. If you go to his site and using this link down here, he has a list of all the groups in the world doing experiments just on trapped ions. And let's see. So anyway, I was just gonna say a little bit about my path to get to these these kinds of experiments, and just so my personal story, try to share shortly with you, is that my parents lived through the Great Depression in the U.S., and that was, there was an economic depression and basically through the 1930s in the U.S., and a lot of people just had lost their jobs, and my parents were lucky or fortunate. They had good jobs, and they were kept employed through this so-called Great Depression. But anyway, from that experience, they always emphasized on me and my sister to, we needed to get a college education, if for nothing else, so we could get a good job. And anyway, but they weren't real pushy about it. And anyway, I liked school, so it wasn't a problem. Anyway, but there was emphasis from my parents on, maintaining good grades in school. And my father, actually, he was a civil engineer, but he he would play mathematics games when I was little ones, like simple things like adding and multiplying and subtracting numbers in rapid succession, in rapid succession, I mean. So anyway, so I was always interested in math. And anyway, so but I had a lot of other interests, and so my parents were certainly allowed me to explore with a lot of freedom what I did, as long as I kept maintained good grades in school. And so when I was younger, I played with model airplanes. Actually, I still play with model airplanes, but that was one of the first things that taught me a little bit about building things. And actually, and in high school, me and my friends were all interested in cars. So I actually got my first car at age 14. I couldn't drive until I was 16, but I bought this car and my father brought it home. And so the next 2 years, it was pretty bad shape. So I had to fix up this car. It was a 1932 Chevrolet there.
Is it one of those hand crank?
No, this was this one had a starter motor. The hand cranks were maybe in the 20s, that was, so they got the starter motors in that case by 1932. Anyway, so actually all through high school, me and my friends we were interested in cars and motorcycles, and anyway, this is a picture of one of the guys' cars. We were doing you can see it's a part here, and we were doing modifications on it and making it into a hot rod. We called it, changing the motor, making a bigger motor, and so on. Anyway, but the thing I would point about this picture is, is that that working on cars together in a group is very much like working in a physics laboratory, I would say, where you're often working with colleagues. And so, I mean, in a way that, this was good experience, because you learn to work in groups that way. So just a little bit about my education. So after high school, I went to undergraduate school at the University of California. My first 2 years were at the Davis campus. University of California has, I forget how many, 6 or 7 campuses, and I went to the Davis one, and it was partly because it was fairly close to where I grew up, and actually, so Davis was then primarily an agricultural school, a very good one of the top ones, and in fact still is one of the top agricultural schools. But anyway, they were trying to build up to teach other disciplines. But anyway, the place to be for physics was down at Berkeley, because that's where there were many high energy experiments going on there, and that was where where the excitement was in physics. So since I was in the system, there was no problem just transferring. I had to fill out a form and show up at Berkeley. And so I went my last 2 years to Berkeley, and I started as a major in physics, but I at that time, pardon me, I started as a math major, but then switched to physics later on. Anyway, then I went to graduate school at Harvard, and my advisor there was one of the most famous atomic physicists of the 20th century. His name was Norman Ramsey, and he and his colleague Dan Kleppner, who later went to MIT, they invented and first demonstrated the first hydrogen masers. And so I think most of the students have some idea about lasers, and masers turn out to be operating on exactly the same principle. M stands for microwave and L stands for light in maser and laser. And in fact, the first devices that demonstrated the laser principle were actually at microwave frequencies, the so-called masers. Anyway, my project was my advisor, he wanted to have accurate numbers of the hyperfine frequencies of all three hydrogen isotopes. So I made a deuterium maser and measured precisely the hyperfine frequency. So then I took postdoctoral position at University of Washington, 1970 and 1975, and that's where my thesis or my advisor there, his name was Hans Demelt, and his thing was his main experiment was trapping electrons. Same kind of techniques, but the focus was on electrodes. In fact, his most famous experiment was measuring the magnetic moment of the electron to accuracies of a part in 10 to the 12. And the reason that's important is that basically the theory can be done to that level of precision. So it's probably the most stringent test of quantum mechanics that there's been. Anyway, so he was famous for having done that. In fact, my thesis advisor as a graduate school, and then as at the postdoctoral position, Hans Stamos, they shared the Nobel Prize in 1989. I'm forgetting now, roughly that time. And they actually shared it with the person I mentioned earlier, Wolfgang Paul, for the invention of the ion traps. So then I went to what's called NIST, National Institute of Standards and Technology. This is in Boulder, Colorado, and you can see the mountains are pretty close by there. And I basically, this is where I've spent most of my career. And now I'm at the University of Oregon, and I think it was reason for my wife has some health problems related to altitude, so that's why we went down to sea level. But I was there. I mean, I was a great group there, and still is this group at NIST. And I think one thing I would say, let me see if I got any here. Oh yeah, let me finish there, and I just would say I think some advice I would give to the students is I think certainly it's a long haul if you end up being a professional physicist or whatever your desire is to do. And I think the thing is, the only advice I would give, and I would it was always true for me, is that I think you want to pick something you're interested in and just don't hold back, go for it. And I think it's a mistake to go into a job just to make money, because you just won't. I don't think you'll get nearly the satisfaction if you don't go into a job that you really like what you're doing. And certainly physics has always been fun to do. So I mean, I don't make a lot of money, but it certainly still is a very nice job. So anyway, that's about it. And I certainly open for questions, but I want to thank you and good luck to all the students in your career. So thanks.
Thanks, Dave. That was good. May I ask, why did you jump from maths to physics?
Actually, that happened in high school. As I say, I was always interested in math, but then in my last year in high school, the senior year, I took a physics class, and I thought it was just really cool the way relatively simple math could explain a lot of the things we see around us. And so that's what got me going. I actually started as a math major when I went to college, just because but then I was taking physics courses, and then I got even more interested then. So then I graduated as a math major from undergraduate. So I mean, as a physics major. So
yeah, I'll thumbs up on that. I find that physics, my love for physics comes from how it explains things.
Yes, I totally agree. Yeah, and I think a lot of it's for, this idea, the being able to explore new ideas. Say in this case for me, quantum computing. I mean, it's really challenging, and you learn a lot of new things in these pursuits. So I think that's the, a lot of the fun for, doing physics. One example for me is that I had this idea of laser cooling when I was a postdoc, but anyway, when I went to NIST, the idea of this of using lasers to cool, in this case, trapped atoms or ions, was important for atomic clocks. And the reason for that is, if in very, very simplistic terms, to make an atomic clock, we're typically capture a large number of atoms or neutral atoms or ions in some device, and we probe the radiation fields like with the maser and the laser. And I think that a lot. Anyway, what I would just say about that is, a lot of challenges in doing doing things. But one of the things. Oops, did I do that? Didn't mean to do that. Let's see.
It's okay, Dave. It's all right.
Okay. Anyway, so I was just going to say that one of the fun things was doing being able to do this first laser cooling experiment. And now there's hundreds of groups that use laser cooling in one form or another in their experiments. So anyway, but of course that was a lot of fun to be able to be the first doing that. So.
All right, Dave, may I ask this? When you do laser cooling, does the laser itself have to be highly single line? Because the laser itself is an atomic.
No, all you want is basically you want the very price, you want precise frequency control. And you need enough power to drive the transitions I was talking about, and that's all you need. There's nothing, the lasers. I mean, they tend to be fairly fancy because we need a narrow line width on the lasers.
Right.
But
yes,
but there's no special requirement other than that. So.
Okay. All right. There's a question on the chat. Any reason for choosing mercury and not other element, mercury ions, for the experiments?
Yeah, that's a good question. The one reason we chose it was it had a very large microwave transition, and then there was one optical transition, and so we could use it to study both the microwave transition. Maybe I didn't say, but the group I was in at NIST, it was a group that makes atomic clocks. So, my career there was spent in part, making atomic clocks, and then later trying to realize some of these ideas of quantum computing. But anyway, we built an optical clock based on this mercury ion, this second transition that I talked about in the experiment. So we could get down to accuracies of frequency accuracies of down below a part in 10 to the 15. And later we moved to aluminum ions, and we can get down to, an accuracy, ability to get rid of systematic effects down to a part in 10 to the 18. And that's sort of the state of the art right now for atomic clocks. So anyway, but the nice thing about the atomic clocks is basically we'd use the same apparatus for the clocks as we would for our quantum computing experiments. So it's fairly easy to make the transitions between the two.
That's on the mercury. There's another one. Are you optimistic that quantum computers will achieve success within the next 5 to 10 years, considering they are still in the early stages of development currently?
Yeah, I don't know that. I mean, it's anybody's guess, but I think I'm fairly optimistic, but it will take a lot of work. I mean, there's been some announcements in the news which are misleading. I think the claims that are made about the status of quantum computing, but I think it's one thing I can say is it's just, I think for all possible implementations, whether it's atoms or ions or say superconducting Josephson junctions or something else. I mean, there's a lot. It's mainly getting the practical control we need over the systems, and I think that that's just going to involve. And it's easier to make a statement like this, but I think in general that's always just involved better and better engineering on the components that are needed. So it may not happen in the next 5 or 10 years, but I wouldn't be surprised if there would people are generating useful algorithms in the next 10 years. But that's just a guess.
On that note, what do you think about the past 1-2 years of activity by IBM?
Yeah, I mean they have a very good system, and they're using for those that don't know, I mean they're using superconducting qubits, and certainly I mean they I mean they have very nice system. It's not clear that that's going to be the winner, but one thing they have done, one thing they did was in the news the last couple of years is I may have mentioned the word, they talked about quantum supremacy. That is, they were able to exercise a quantum algorithm, a particular algorithm that they could do more efficiently on their quantum system, their superconducting Josephson system, than a classical. They could do it faster than, in fact, a classical computer could. And the only problem there was that the algorithm that they invented had no practical use. So, but I think I would say I'd be very optimistic within the next 10 years that one of the quantum computing implementations will be able to do an actually useful computation. In fact, a lot of us I think this idea of factorization, because it compromises the popular encryption systems. That problem basically goes away because now there's Peter Shor, this fellow that I mentioned, invented the algorithm for factorizing large numbers. He says what he says now, the classical cryptographers are coming up with algorithms that as far as he knows, a quantum computer can't crack. So in a way, that problem will go away. But one thing, for example, that chemists talk about, quantum chemists, is that is the idea maybe you could, if you could synthesize the action of some molecule, let's say, might be used in some kind of drug therapy, let's say, and if they could simulate the action of that molecule on a quantum computer, before they had to synthesize it in a lab, that would be wonderful. And that's kind of a pie in the sky kind of thing. But I think that quantum computers will eventually find a use that way. They'll be able to check how a certain system works without actually having to synthesize it in the lab. So
that's still far away then. All right. Do physicists work on finding new quantum algorithms that might solve new problems?
Well, I think that was what I was trying to address there. That I think there. Yeah, and
there is one by a very young person here. Can I know how to get your effort or research done by the Nobel Prize or research? I suppose, can I know how to get your effort or research recognized by the Nobel Prize organization? And do they help you to get patents or rights?
Oh, I see. Well, I don't think I don't think anybody's gotten any direct help from the Nobel Prize committees, for developing something, a commercial device or something like that. So, but I think, it's certainly, there is a certain reputation that goes with people who have received the prize. And so I think that's always a good starting place. But I think the thing to say is that just in general, I don't think you should go into physics or some other field, to win a prize, and like say the Nobel Prize in physics. I mean, you should go into it because you like it, and I think that you like the work.
Yes.
And I think that look, I know in my case, I mean, the chances there are a lot of other talented atomic physics people out there that could have received the prize rather than me. But my main message, as nice as that was, I think the main reason you want to do it is because you like the work, and that'll be the main reward in the long run, I think.
All right. There's another one here. Do you think it is possible to use an AOD to move ions around inside? I'm not sure what is an AOD. AOD.
I don't know either, but
What's AOD? Quack. Dr. Quack, if you're around, you can use your mic. What's AOD?
So hi Dave. Thanks for
Hi.
the talk. What I meant was the experiment by Michel Lukin, where they moved the atoms around with acoustic optical modulator.
I see. Yeah, sure.
Deflector.
Yeah.
So I was wondering whether one could eventually use the same technology on ions instead. Then in that case, you don't have to put it on the channels, right?
Yeah, that's right. In fact, there's a recent proposal, a paper that hasn't been published yet by one of my former colleagues who's now in Israel. But anyway, on using those same ideas, the neutral atom guys call it atomic tweezers, where they can hold on to.
That's right.
Yeah, and so those ideas are, at least, as I say, there's a recent paper that's talks about exploiting that idea for ions as well as neutrons.
Okay. So then you can change the topology altogether.
Pardon?
You can change the areas, the regions where you move the atoms around.
Yeah, that's right. I think for ions, I think he would still probably, I mean, it's hard to see how you would do things unless you have kind of the same structure I was talking about there. But just in terms of moving the ions around to different locations, that, the idea of using optical tweezers looks, really interesting. So that may be a much better way than we do now.
Great. Thanks. I've got to go back to another meeting. Sorry.
Thanks, Dr. Craig. Thanks for joining. There's another one here. Shaw's algorithm, Grover's algorithm are mainly tackling cryptography. Is there any other use case of quantum computing that solve other kinds of problems?
Well, I think that I think there's, at this point, there's no really notable ones like that. I think as a group, I think we're headed there. For example, this example I gave of maybe synthesizing action of a molecule before actually having to synthesize it in lab. I mean, I think there'll be experiments like that. I should say also, there's a lot of in business, which I'm not very, there's optimizing algorithms and things like that could be done more efficiently on a quantum computer, but I'm not the one to talk about those. I don't really have much knowledge of those kind of algorithms.
Okay. Quite interesting questions coming up now. Until now, there haven't been significant experiments with large number of qubits demonstrating quantum advantage or supremacy. How many qubits are required to achieve quantum advantage over classical computers?
Oh, I mean, that's sort of a difficult one to answer. I mean, it could be,
depends on the problem itself in the first hand.
Yeah, and I don't know whether I can get a good answer to that, because you know, it isn't clear, you know, maybe one physical platform will be better, you know, to solve certain problems than others, but I don't think I can give a good answer to that. You know, at the stage we're in right now, though, I think there's, you know, the viable, you know, systems are maybe ions and neutral atoms as well, but then various forms of Josephson junction devices. And so I think, you know, there may eventually be a big winner, but I don't think we know which technology that's going to be yet.
There's a big gun pointed at you, Dave. Ion trap mass spectrometer has been around for quite a long time. What are the differences of your ion trap for quantum computer versus ion trap for mass spectrometer?
I think that the main differences, in fact, I mean, we use some of the same basic ideas. The ion traps that I was focusing on, they can, you know, they can do mass, be arranged so they do mass separation and things like that. So I don't know. I mean, as I say, you know, the same basic technology can be used. In fact, there's mass separators that work on the very, you know, arrangements of electrodes very close to what I described that in the first part of my talk. So and anyway, I think, you know, there are those applications. Yeah.
Okay, now there is one a bit off going towards education. Thanks, Professor, for your valuable insight. As a student aspiring to pursue a career in research, I'm keen to understand the key attributes and experiences that contribute to a strong foundation in research. Could you please provide guidance on the essential skills, knowledge areas, or specific steps that you believe are crucial for a student to focus on in order to establish themselves successfully as a researcher?
Well, I mean, it may be a little different in different fields, but perhaps, you know, what I can say about physics is not so much different than other technical areas. But I think, you know, as you're in school, you want to be able to you know, soak up as much, do as well as you can in your classes, because that'll be important in your future work. And the one thing I can't maybe speak about all fields, but the natural thing in, you know, for students that are interested in physics is, you know, even as undergraduates, they can start to get involved with groups, you know, doing serious research. And so I think, at least it's certainly in the US, that's true. There's a lot of programs that will integrate, you know, undergraduate students into research, and, you know, so they get a flavor, get an idea of what real research is like. So I don't know whether it's true, but there may be similar programs in Malaysia and other nearby countries there.
Okay, thanks for the great sharing. Recently, I was studying the current landscape of quantum computing. Based on that, I would like to understand if there is any widely recognized metric to benchmark quantum computers from different technologies and different hardware providers. I'm thinking in line with how to benchmark current classical computer performances. I suppose.
What was the characterized? Just what? Say it again. Characterize what?
I'm thinking in line with how we benchmark current classical computer performances. That means he would like to know if there's any widely recognized metric to benchmark quantum computers from using different technologies.
Yeah, I would say I'm probably not the best person to ask, but I would say, from what I've seen, I would say there's no, you know, obvious way to demonstrate their properties. I mean, even this IBM algorithm, even though, as I said, it wasn't really do anything useful, I think those experiments are important because they show, you know, they could do complicated things, and so you know, I think any of those experiments are important. I mean, you certainly see cases where the achievements are oversold because they're, you know, but I think the companies are trying to get money that way. But anyway, that's probably true in any field. But to try to answer the question, I don't think there's any set metrics, you know,
Most probably it's a bit too early.
Yeah.
We need to let the technology mature itself, and then maybe then the metrics will come in.
Yeah, I think that's right. Yeah.
Yeah. All right. Now there's another big gun. Quantum Advantage in Learning from Experiments by Xin Yuan Huang et al. Has proven that QC experiments with up to 40 superconducting qubits and 1,300 quantum gates demonstrated that a substantial quantum advantage can be realized using today's relatively noisy quantum processes. Do experimental physicists recognize this achievement?
Well, I mean, again, I'm probably not the one to ask, but I would say, you know, one of the outstanding results that I mentioned was, I think it was IBM that did this, you know, this came up with this algorithm that they could do much more quickly on a quantum computer. And the one I'm thinking of is it didn't really have any practical value, but I think just the way things are progressing, I think there will be these algorithms that can be done very efficiently on some quantum computers that that are really useful. And I think it's just natural that I think that's going to happen. I would say it hasn't happened yet, but I think it will happen.
What new or upcoming technologies that you foresee will be useful for trapped ions to achieve fault-tolerant computation via quantum error correction?
Yeah, I think it just comes in the technology of, people are making, for ion traps, people are making better and better ion traps where they can get better and better control. So I think in that case, I'd say, big factor is just the engineering part of it. And because I think we know, we have basically the plan for how to do things, and just making the instruments, work with, higher fidelity and things like that. I think that's part of the issue. So, I mean, that's a hard question to answer, but I think, people are always making improvements on whether it's ions or superconducting devices. The improvements are steadily coming, and so I think the field will certainly continue to progress. And who will be the most important? What will be the most important? Platforms is not clear yet. I think that they're all contenders, but it's too early to say, I think.
Okay, Dave, there's one last one I think is, I suppose is quite nice. How do you address issues such as decoherence and quantum noise in your experiments? And what strategies do you employ to improve the coherence and stability of quantum systems?
Yeah, I see. Well, in the case of ions, I think, it's been important to go to low temperatures. You can certainly freeze out thermal noise, and actually one of the things in the experiments on ion traps that are related to this question is one of the problems we have is that we notice that the ions, there's some heating source, it's some apparently white noise electric fields that are heating the ions, and what exactly the detailed reason for that is, of course, I should say that heating is bad because, for example, it could change the motion quantum numbers, which interfere with things. And so one of the things we on a little side project when I'm at this project still goes on was the idea, we were seeing heating which we couldn't explain, And so what we, we had just conjectured that maybe it was, some kind of molecules or atoms wandering around on the surface of the electrodes. And or maybe even patches of oxide or something. And so one kind of crude experiment we did is we had an ion trap, and we'd measure this heating rate, this sort of broadband heating rate effect. And what we did is we cleaned the electrodes with an argon ion beam. I mean, it's a standard technique to clean metal surfaces with an argon or ion bombardment. So we subjected our trap to some ion bombardment, and the heating we were seeing went down a factor of 100. And so I think it was good indication. We don't know exactly what was causing the problems, but I think presumably we're getting rid of some surface contamination on the electrodes, because it was really a dramatic change. And gradually it would get worse if we just left, didn't do anything. But we could always come back. We could re-clean the surface by this ion bombardment. And anyway, so that people are seeing those effects, and how we get rid of the stuff we have on the surfaces. We don't even know exactly what it is yet. So,
Hey, Dave, one last one. What are the main statistic measure analysis in quantum computers for testing performance and effectiveness, accuracy, and reliability of quantum transformation? Statistics
I'm not
measures.
sure I understand the question.
I'm not either. What are the main statistics measures analysis in quantum for testing performance?
Well,
computers for testing performance and effectiveness, accuracy, and reliability of quantum transformation, or statistical measures, statistical analytical methods.
well, I don't know whether I know how to. I'm not sure I can answer that question very well. As I say, the kind of things we see that are harmless is, and we several groups are working on this, is why do the ions get heated up? And we know now that just what I mentioned, the thing about using argon beam cleaning, it points to the fact that this stuff gets on the surfaces that we can't control. And so I would say, when you talk about statistical fluctuations, I think those are the main statistical fluctuations in our experiments, are the noise that's heating the ion motion. Anyway, maybe that's too simple of an answer, but certainly the big effect for ion traps, I would say.
All right, Dave, I think we won't hold you much longer. We just require you a few more seconds, few more minutes. Sure. Take a group photograph. Thank you very much for that talk and opening up a whole new field for us. Now for a group photograph, if everyone could please switch on your cameras, please. Could you all please switch on your cameras? Could you all switch on your cameras, please? Cameras. It's just like touching the subscribe button in YouTube. Just switch on the camera. All right, Ms. Valentine, you asked the question. Please switch on your camera. Or is it Mr. Valentine? Are we done? Secretariat? Okay. All right, nice. Okay, again, thanks, Dave. Have a good evening. Thank you for that talk.
No, I was happy to do it. And as I say, I wish students all good luck in whatever they pursue.
Yes. Thank you very much. We will, Dr. Nazri and the secretariat will be in touch with you later on for certs and all that.
All right. Well, anyway, yeah, thanks.
Again, thank you, Dave, and very happy birthday soon.
All right. Thank you.
Okay, bye.
Bye-bye, everybody.
Bye.
Happy birthday,
Yeah.
Steve.
All right.
Birthday.
For all other people, there will be a QR code flashed